Good morning, everyone.
Good morning.
Good morning, ma'am.
Can you hear me? Can you see the screen?
Yes, ma'am.
Should we start our discussion? Yes, very good morning. Should we start our discussion? Fine. So, yesterday, I still remember, students, we have asked you a question. Did you find out that black phosphorus is the most stable allotrope? But black phosphorus is also a beta black type and alpha. Very good. It's the alpha black. Yesterday, I got the answer. Yes. But I still wanted everyone to ensure that actually helps you study and find out something you read because of that. That's again an added advantage. Fine. Okay, fine. So let's continue our discussion with the oxides of phosphorus. We'll start with phosphorus trioxide, P2O5 or P4O6. Preparation. Very simple. When you burn phosphorus in a limited supply of air or oxygen, phosphorus trioxide is formed. In limited supply of oxygen, P4 reacts to produce P4O6. Now, properties. When you heat it in air, means you supply more oxygen to P4O6, it becomes P4O10. The structures we had seen in the last class. Fine? Yeah. Before continuing further, yes, it is still like that. Before continuing further, I thought I could see some space here. And why not ask you people a question? Give me a minute. Wait. Okay. I will give you NaNO3. Heat it. What do you get? AgNO3. Again heat it. What else? I will give you NH4NO3 and NH4NO2. Yeah, we discussed some of these yesterday also. Okay. Faizan, there's a small mistake here in the first one. No, small, that's incorrect. NaNO3 is decomposition. I do understand it's from his block. That doesn't matter when we discuss questions. AgNO3. Okay. You missed one more thing there. Okay. This one, I will write these two first. Yesterday we did N2O
Yes.
and H2O. Yes. NaNO2. The moment I get correct answers, I'll start copying from your chats. No. Jokes apart. Yes. If it's lithium nitrate, on heating it decomposes giving Li2O, NO2 and O2. We have to see the balancing. It will be balanced. If I take 4 here and etc. I think so I can take here 4, here 2, here 4. So lithium is balanced, nitrogen is balanced, and 8, 9, 10, 11. Perfect. The equation is balanced. So if it's lithium nitrate, on heating the thermal decomposition products are the next important thing for your exams. So if it's lithium nitrate, it decomposes giving Li2O, NO2 and O2. Fine. But if it's NaNO3 with sodium nitrate, it is not Na2 NO2 and O2. It gives you NaNO2 and O2. It gives you nitrite and oxygen, and this gives you oxygen plus NO2 and oxide. Yes, you are correct here. In the chats, the people mentioning in the chats, you people are correct here also. AgNO3 gives Ag plus NO2 plus O2. You have to balance accordingly. Yes, perfect. I got all the products correct. Which means at least one work I have started doing now for group 16. Yeah, I know group 15 is not over. One job I've started doing for group 16 as well. The preparation of O2. Year. Preparation of N2 for group 15. Done. Very good. Very good answering. Let's continue with our discussion. Now, we have P4O6. When it reacts further with oxygen, it produces P4O10, phosphorus pentoxide. Let's talk about P4O10 now. When white phosphorus is treated with limited quantity of air or oxygen, P4O6. With excess of air or oxygen, we get P4O10. Yes, the structure is already there here. We did this also. So when anyone watches something again, so little brief or recap from the previous class is much required. Students, metaphosphoric acid, HPO3. Can anyone recollect? It can exist as a polymer. It can also exist as a cyclic trimer. Will you agree when I draw it as POH? O. Wait, how will we link it? PPP. POP. And then we have 4H justified. HPO3 whole thrice. So, yeah. So I have, yeah, trimetaphosphoric acid. Yes, the cyclic trimer. I was actually trying to draw it. Let's see. So I have should have 3H justified, 3P justified, and 9 oxygens. 1, 2, 3, 4, 5, 6. Okay. 7, 8, and 9. Now it's okay. Trimetaphosphoric acid. Yes, correct. And let's find out the hybridization of this phosphorus here then. 1, 2, 3, 4, sp3. Perfect. No. It's just not sp3d because the pi will not be counted under hybrid orbitals. 1, 2, 3, 4. Has to be sp3. With hot water, it gives phosphoric acid. Very important. P4O10. When you add cold water, metaphosphoric acid, see the formula HPO3, mostly exists as its cyclic trimer. As I have just mentioned, it's sp3 hybridized, and with hot water, it gives phosphoric acid. Yes. Phosphoric acid is pretty simple to draw. Again, sp3 hybridized. Everyone, So the thing should get registered here in the class itself. With hot water, P4O10 gives phosphoric acid. If it's cold water, P4O10 gives metaphosphoric acid. HPO3. Metaphosphoric acid, H3PO4, normal phosphoric acid. Let's continue. You know very well, though we mostly call it P2O5, that P4O10, that's the dimer of P2O5. Fine. It acts as a dehydrating agent. So P4O10 will remove water from perchloric acid and form Cl2O7. So it acts as a very strong dehydrating agent. Students, in organic chemistry, can you remember any reaction where P4O10 is acting as a dehydrating agent? Let Even I have also asked the question right now. I could recollect one reaction and one more. Exactly, anhydrides was in my mind. Yes. Let's see the space first in the slides and this one too. I'm sorry. Once again. Yes. Absolutely. When someone wrote no to formation of anhydrides, should be honest, no. I That's the first thing which came to my mind, and these two molecules of acetic acid came to my mind. We can take anything. With P2O5, mostly we write I can write P4O10, but mostly we write P2O5. You also know, right? You'll agree. When we heat it, it loses a water molecule, CH3, CO, O, CO, CH. Yes, anhydrides are formed. Have a look here also. Amides. Remove the water there, H2O. Amide, CH3, CO, and H2. Remove H2O. What you get? Today she is writing P4O10, otherwise she'll write P2O5. True. Remove H2O. We get this. Fine.
Yes, ma'am.
One more question then. Fine. Um, the question what I wanted to ask is, and this reaction will come again and again and again, is when iodine reacts with Na2S2O3, it produces NaI plus Na2S4O6. I would like to maybe I'll write it in a little better way. I would like to know the N factor of iodine plus sodium thiosulfate in this reaction. Students, I was going through so many things in group 16 and I saw this person coming again and again, and it's needed in redox. So I thought, why not ask you people? And if you don't know, I would like to discuss it. I2 plus Na2S2O3 gives, just give me a minute. Once again. Sorry, I got a call from the organization only. So I had to pick up regarding some class. Already one class is going on, some other class. Anyways, so sorry, I had to pick up. I2. So help me out. 2 for I2. Very good. See, I2 gives I minus iodide ion. So the iodine atom should be balanced on both the sides. I2 gives I minus. The iodine needs to be balanced on both the sides. For that, I'll place a 2 here. First, the atom which is undergoing a change in oxidation should be same on both the sides. Fine. So 1 iodine oxidation number is 0. 2 iodines. 2 into 0, 0. 2 into minus 1, minus 2. So basically 2 electrons are being gained per molecule of iodine. I agree. 2 is the correct answer. 2 electrons are gained per molecule of I2. Next one I want from you people. I've given the products also. So in fact, you'll need it in redox also in case you don't know. Definitely I'll continue with inorganic only. N factor of I2 is 2. Na2S2O3. I have to put 2 Na2S2O3. Why? To balance sulfur atoms. You can tell me the answer. I'm doing it slowly so that during the discussion also get some more people answering. Na2S4O6. Sodium tetrathionate. Now what will we do? Very good. I got the answer, Susan said. Very good. So here one sulfur is plus 2. But I have total 4 sulfur atoms. 2 twos are 4. So 4 sulfur atoms will have total plus 8 charge. Here the oxidation number, if you use the formula, you'll get it plus 2.5 or 5 by 2. So that's per sulfur atom. So there are 4 sulfur atoms, each with an oxidation number of 2.5. So the change in oxidation number is 2 for 2 molecules of sodium thiosulfate. Yes, you people are correct. So 2 electrons are lost by 2 molecules. So per molecule, number of electrons lost is 2 by 2. That's 1. So n factor here is 1. Just wanted to mention so that it will come again and again and again. Yes. Yes. Vaidehi, Shri, and Faizan and others. Anyone having any difficulty here, let me know. Otherwise, right now our discussion was oxides of phosphorus where P4O10 is a very strong dehydrating agent, and that reminded me of organic reactions where formation of anhydrides or nitriles or these anhydrides. This perchloric acid, and that's the anhydride of perchloric acid obtained by using P4O10 as a strong dehydrating agent. Fine. Let's continue then. Phosphine. Phosphine. Students, if phosphine is pH 3, I told the easy one. What is phosgene? Yes, I'll Faizan, I'll go for heating of P4 with NaOH solution to get Na2HPO2 plus pH 3 as we saw in the last class. Fine, agreed. But I'm asking you something else right now. Okay, and I got the answer. Atika mentioned phosgene is the poisonous gas, and that's formula is COCl2. It's okay, very good, good preparation. Whatever you ask, you all are ready. Phosphides on hydrolysis liberates or produce phosphine gas. Students, what do you think? Which is more basic, ammonia or phosphine? Ammonia, perfect. Whatever you ask, everyone is ready. As mentioned yesterday, Only one of the hydrogen in H3PO2 is replaceable, so it's NaH2PO2, and that's a lab method. It's a disproportionation reaction we discussed yesterday. The hydrolysis of calcium phosphide produces phosphine. Properties: highly inflammable, weakly basic, just like ammonia, and not like ammonia, it's still less basic than ammonia. Ammonia is a weak base. Ammonia solution NH4OH is a weak base. This is still weaker base, as discussed yesterday. When absorbed in copper sulfate or mercury chloride, corresponding phosphides are obtained. Fine, not so important point. You learn well and good. The corresponding phosphides are obtained when you take a sulfate salt or a chloride salt and treat it with phosphine gas. Important one is the preparation one. In case I have to mention this, this preparation reactions are much more important. Uses. Why pH3 is less basic? Sure. Um, NH3, please feel free to ask. I think so. I'm also added in your Telegram doubt group. That's what I saw today. You have any difficulty, you have any confusion anywhere, please feel free to message me there. Okay, I've shared my number in case somewhere not there. Nitrogen is small in size. The orbitals are also small. The sp3 hybridization which occurs here involves small orbitals. So there's a very compact arrangement. One lone pair has to be there. One lone pair has to be there. Say, for example, there are 10 seats in a classroom. Fine, and you're alone there right now. So you take the liberty to sit anywhere you want. And suppose in one particular subject you sit here, the other one you sit there, and that also liberty you people just take. A very free arrangement when you have a lot of space. Here, that's not the case. Very compact arrangement, small size. Compared to that, the orbital here, if we consider Drago's rule, this would be present in a pure, in a pure. Anyways, not confusing you more. This is quite large. The same one lone pair. One seat for one student, and the person has the right to only sit there. Well and good. Very sure shot arrangement. The next day I try to find out the person. I know he'll be sitting in this particular classroom, this particular bench, this particular place. Done. Here, the same one student, and there are many more seats. It's much more spacious. So exactly you cannot guarantee where the person will sit. Got some idea? You
Yes, ma'am.
definitely, I know he'll be here or here or here or here, but not for sure that it will be sitting in that particular place where you want. So here this is very scattered arrangement, a very compact arrangement. It's very scattered arrangement. So the availability of the lone pair is more here. You sure shot, you know the person is sitting here. Go and do this work. Go. Here it's more scattered. So its donation ability will be comparatively less. Ask Nandana if it's still not clear.
Ma'am, like these lone pairs are closer to the nitrogen
When
atoms.
there
It's
is
like,
an lone pair present in a particular orbital, which is having a very compact arrangement, sure shot it will just do its work and done. But when now not only pH3, though only it's slightly only very slightly less basic. You go down till bismuth, you will see that bismuth has a huge mansion made for just one lone pair. So the lone pair is quite scattered and not very compactly present. So when its turn comes for donation, it becomes still lazy and doesn't do its job so effectively. Please ask. Okay, sure. Please, most welcome. Feel free to ask your doubts. Phosphorus will form PCl3. Okay, if we consider Drago's rule, if we and he got a Nobel Prize, etc., etc., so we have to look into that. So if we consider Drago's rule, then PSH3 and ASH3 and SBH3, etc., etc., the lone pair should reside in a pure S orbital. S orbitals are closer to the nucleus than P. Yes, I will have to agree. See, actually, I'll tell you, students, these explanations why you find different in different places because experimental value is known for they'll calculate pkb for these bases and then we know the basic strength decreases and then we'll try our best to explain the things in different way. I will definitely go with this explanation also. I will agree if we apply Drago's rule where the central atom should have at least one lone pair and it should be bonded to a less electronegative element and the electronegativity difference there are also some conditions and the element should belong to third period onwards, not the second period, etc., etc. 90-degree bond angle, yes, so much. So in those cases, we'll assume if we have to apply Drago's rule here, we'll assume the lone pair to be present in a pure s orbital, s closer to the nucleus, more penetrating power. So the electron would be reluctant to donate, like reluctant to behave as a Lewis base. I will, I'm so tightly bound to the nucleus. I am not that much available as the lone pair in NH3 and hence NH3 would be more basic. Agreed. Very good. Coming back, so many things are there. So, these are some of the methods to prepare PCl3. They can directly make P4 react with chlorine. What's the name of SOCl2? Very good. Thionyl chloride. The moment before I utter, very good. Thionyl chloride. What about SO2Cl2? Sulfuryl chloride, no? Very good. This is thionyl chloride. So P4 with thionyl chloride, P4 with chlorine produces PCl3. When it gets hydrolyzed, the three chlorines will be replaced by 3OH and H3PO3. This phosphorus acid will be formed. I would like to know the impact of phosphorus acid. It's very important for us to know this. Very good. So there's no confusion that H3PO3 is phosphorus acid and its n factors too because only these two hydrogens are directly attached to highly electronegative oxygen atom. So when I'm discussing this, why not quickly discuss that H3PO2, which is hypophosphorus acid. We saw it very quickly. That's the reason. Its n factor is 1 because it contains only one replaceable hydrogen atom. Yes, H3PO2 contains only one replaceable hydrogen. H3PO4 everyone knows. So I will not ask this question to anyone. You want to type it? Well and good. Good. When excess of chlorine is present and P4 reacts with it. Yes, very good. I saw the chance. PCl5 is formed. Students, this PCl5 and PCl3 is required for a reaction of in organic chemistry. Organic chemistry. ROH plus PCl5, ROH plus PCl3. Yes, SN2 mechanism. Yeah, with alcohols to produce the respective alkyl halides. it- we have to take care that the substrate should not be statically hindered so that SN2 can happen smoothly. Very good. Yellowish white powder when it gets hydrolyzed. Compare the hydrolysis product of PCl3. When it gets hydrolyzed, you get POH whole 3 with same as H3PO3 and HCl. But when PCl5 is hydrolyzed, again same SN2, you can show. Very good. You get POCl3. I would like to know the hybridization of phosphorus in the hybridization of P in POCl3. Let's see. Ah, super fast. Very good. But when POCl3 is further hydrolyzed, it produces H3PO4. Yes, POCl3 is like this. You're absolutely right. So first PCl5 gets hydrolyzed and we get POCl3, which on further hydrolysis produces H3PO4. We always study in equilibrium about this reaction, no? Needless to say, PCl5, getting my point? Splitting into PCl3 and Cl2. Where we have to give examples of delta Ng positive and do certain explanations, we take this equation. Acha. Chalo, tell me, when you add inert gas at constant pressure, when this system is at equilibrium at certain temperature T, and now you add inert gas at constant pressure. Forward or backward? The equilibrium will be triggered in which direction? Think. Very good. All except one or two. Think. Students, I have an equilibrium between PCl5, PCl3 and Cl2, as you can see. I am going to add some inert gas in this reaction mixture which is already at equilibrium so that I can disturb the equilibrium. I'm not disturbing the temperature is assumed to be constant. Now, when some inert gas is added at constant pressure, volume increases. So when V increases, N should also increase so that the N by V ratio remains unchanged. When V increases, N should also increase so that this ratio should remain unchanged, and so the reaction should move in a direction where the gaseous moles are increasing. Yes, Vaidehi, forward. So N should also increase. If, if N should increase, the reaction should move in a direction where the gaseous moles are increasing. Forward. Very good. Agreed. Very good. Yes. So you can see that PCl5 basically prepares or produces acid chlorides from acids. Yes. Very good. Today Suman is also interacting. I have now remembered some names like Vaidehi, Shri, and Faizan, and many more. Arpita, and one more with a Suman. Please feel free to interact and yes, discuss with me. Yes. Atika, forgot this name. Yes. So PCl5 will produce CH3COCl, means acid chlorides from acids. From alcohols to alkyl halides. So to prepare acid chlorides, alkyl halides, this method can be used. I will not say anything about this. We said enough. Now, we'll move on to, we also discussed about metaphosphoric acid, which is very stable in the form of its cyclic trimer. Diphosphoric acid or pyrophosphoric acid. Let it come, but I'll explain it in my own way. I do this. I'll take a normal phosphoric acid. I'll take one more phosphoric acid. And I will remove a water molecule. I'll take a phosphoric acid. I'll take one more phosphoric acid and remove a water molecule. And what I get is H4, P2, 1, 2, 3, 4, 5, 6, 7. I get this. So since I prepared it basically the way I prepared anhydrides, so definitely I can expect that the phosphorus oxidation number will be same plus 5. Yes, H4P2O7. And can I expect the oxidation number of phosphorus to remain unchanged, or as the oxidation number of H2PO4 is plus 5, similarly the oxidation number of H4P2O7, in that also phosphorus is plus 5. Yes, you can check. It is plus 5 each. And I hope you also know that logic, right? Where you assign, or you, if this is more electronegative, you put -1 here and +1 here. Again, there are two bonds in which each is more electronegative than phosphorus, oxygen. So I can put -2 here, +2 here. In case you're not aware, let me know. For this oxygen and phosphorus bond, -1 here and +1 here. For this phosphorus oxygen bond, -1 here and +1 here. So if I add up, I get +5. That way also you can check. Fine. And needless to say here, phosphorus is +5, +3, and +1 oxidation states respectively. Clear now, everyone? Moving too
Yes, ma'am.
fast. Lots of inorganic stuffs are there. That's what I got to know. Understood? Clear? No doubts? Now you try H4P2O6. It was there, no, in that slide. What strategy should we adopt here? First, find out the oxidation number of phosphorus here. It's there, but without looking, what should we do? H4P2O6. The oxidation number of each phosphorus. Okay. And the structure. OH, 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 O, O. Yes. So P should be +4 each. Oxidation number is always calculated per atom. So the oxidation number will be +4. And this will be the structure. Fine. Agreed. So yes. And it is known as hypophosphoric acid. And when we do it on our own, we find it like more comfortable. The basicity here should be 4. Here also the same thing. But yes, yeah, fine 4. But we'll hardly get such questions. You also know that. Anyways, the hybridization of this phosphorus, you should know drawing the structure. Remaining all should logically come up. sp3, 1, 2, 3, 4 sigma bonds. I can see sp3. Will you agree? Yes. Fine. The next one. So Monday, can I expect to that I can ask you people some questions on this P block? Yes. By the way, H3PO5, H4P2O8. Use the formula and find out the oxidation number. Plus 3 plus X plus 5 into minus 2 is 0. And what are you getting is? Are you getting plus 7 here? Yes. But what's the thumb rule? The thumb rule is an element cannot ever exceed its highest possible oxidation state. And we are exceeding it theoretically because we have already assumed that all the oxygens are present in the form of oxides. That's not true. Some of the oxygen here is present in the form of peroxide linkage. H3PO1, 2, 3, 4. Wait. 5. Yes. It's because these two oxygens are present in the form of peroxy linkage and each oxygen will have -1 oxidation state. That one will not know if they apply the formula without knowing the structure, and hence if theoretically you are getting such an answer, this means that an element can never cross its highest possible oxidation state. This is because you're assuming something wrong when you are calculating. You're assuming all the oxygens to be -2, which is not true. Three of them are -2 and two of them are -1 each. And hence, if such a thing occurs, cross it, cut it down, and just write it as +5. So if an element exceeds its highest possible oxidation state, it's because of some this kind of theoretical errors, and you can cross it and write down instead the highest possible oxidation state. That yes, yes, peroxy linkage, POOP, POOH, and here you'll get POOP. What POOP you're talking about is yes, Vaizan, you'll get it. Yes, yes, peroxy linkage, peroxide linkage here. Similarly, when you apply that formula in the second case, H4P2O8 plus 4 plus 2x plus 8 into minus 2 is 0. 2x minus 12 is 0. It's not possible that phosphorus becomes +6 suddenly. It's because you have not considered this as peroxide and oxide. You will cross it and just mention +5. So, what's the moral of the discussion? It is an element cannot have oxidation number greater than the highest possible oxidation number. That's not possible. And hence, in each case, P is +5. We have already drawn all the correct structures. You can find peroxy linkage in both these structures. So, concentrating on the oxy acids of phosphorus, sulfur also, but that in group 16 is very, very important, relevant. Okay, basicity, no problem if it overlaps. I'll write it here 4 and here, of course, 3. Metaphosphoric acid. Either it exists as a polymeric unit, as I was telling you, but it's more stable in the form of its cyclic trimer, which we have drawn. And I've mentioned that the hybridization of the phosphorus here is sp3. Students, though I know we'll discuss this when we discuss sulfur, can you help me with H2S2O8's structure, oxidation state on the sulfur, and what all? What else? Hybridization. Okay, okay. I got the answer. At the same time, let's also draw, since it's group 15 going on and it's getting over, the structure of HNO2 and HNO3 before proceeding to group 16, which also will start right now. SOOS, OH, OH. 1, 2, 3, 4 I wrote, and 2 hydrogens I wrote. Let me count. Wait. 1, 2, 3, 4, 5, 6, 7, 8. H2, S2, OH. Yes, sulfur in the plus 6 state. And its hybridization. Just count the sigma bonds around it. You will realize that it is very good. The next task, yes, yes. Very good. The next task is to draw HNO2 and HNO3. Let's draw it. If we memorize, we can never remember for a long time. If we logically deduce, HNO2 over. Wait. Mm, HNO3, HNO2. Convinced. I'm convinced. Hybridization. Wait, wait, wait. Yes, yes, yes. I got the answer only. So this is HNO3 and the nitrogen is sp2 hybridized. Okay. HNO3. Let's first look into HNO3 first. HNO3. So nitrogen is sp2 hybridized. It has a double bond O, a coordinate bond with oxygen because nitrogen cannot have more than 8 electrons around it, and a OH linkage. So think this at the center and this one, and this one as the like three parts of a three corners of a triangle. So this is justified. Now, can you help me here? Is it justified? No problem, no? Comment on the hybridization of this nitrogen, but sp2 only, right? A lone pair, 2 sigma bonds. So HNO2 one can be rewritten as, no, it's correct only. To show it little sp2 hybridized, would we take the pains of writing it like this and putting a lone pair here and O, same thing, right? Yes, very good. So give me a minute. No, no, I'm not going anywhere. I'll just change the slide and we'll go to group 16 slides. So I'll stop sharing for that reason for a while. Yes, I took a while so that we can start group 16 as well. Tell me which one has higher electron gain enthalpy, oxygen or sulfur? Oxygen or sulfur? Sulfur, right? Because oxygen is small in size, so the electrons already present in their valence shell is already facing a lot of repulsion. A new member in, and it would do more ragging. Joking. So the new member would face extra interelectronic repulsion because an extra electron is being added in the small compact area. Fine. So here we let's start group 16 of the oxygen family. It's oxygen, sulfur, selenium, tellurium, polonium, and livermorbium or something. Wait, livermorium. Okay. The new element. As I told, I always follow that IUPAC rule for atomic number greater than 100. Fine. The first two are nonmetals. The next two metalloids and polonium and livermorium. Though we are not going to study and say bye bye after this slide to livermorium. Polonium is a metal. Fine. Now, students, livermorium or great Shefali. Yes. Oxygen, due to its small, tell me some anomalies or special properties of oxygen. First of all, its physical state is gas, while others all are solid. Oxygen, due to its small size, and basically this is the characteristic of all second period elements. Because of its small size, it can form not only a strong sigma bond, but the additional pi overlap or the sideways overlap is also very much feasible. Yes. Again, yes, it doesn't contain a d orbital, so it can't expand its octet. So someone wrote non-expanded orbital. Yes, can't expand its octet because it doesn't have a d orbital in it. Yes. Okay, second most. I was reading most, Vedeshri. Yes. Second most electronegative member or element of the periodic table, I will agree. And the most electronegative element is fluorine. Yes, the most electronegative element is fluorine. And yes, you're right. I didn't read that second most. The most I was reading, yes. So second most electronegative element is oxygen. So due to its high electronegativity, very high, the second most you can understand, 3.5 is its electronegativity value on Pauling scale. Okay, so due to its high electronegativity value, small size, absence of d orbitals, it behaves differently. And the first different behavior, its physical state as a gas. O2 exists as a stable molecule because of the very strong, quite strong pi bond formed due to sideways overlap of the two small 2p orbitals. So O2 can exist. S2 will be highly unstable. On the other hand, p pi bonds. Correct. Yes. Sulfur, on the other hand, wants to remain as a king or a queen, whatever. One, two, three, four, five, 6, 7, 8. So this is the way S8 exists. S8. You can see how they are bonded by strong sigma bonds. On the other hand, S2 will not be stable because 3p overlap, 3p pi overlap, sideways overlap would be not that stable. But on the other hand, if it's a PD overlap, like your PP overlap, well and good. 2p by the way. 2p by the way. If it's a 2p 3p overlap or 2p 3d overlap also justified. But if both orbitals are 3p 3d types or 3p 3p types, the size becomes too large and the effective sideways overlap doesn't take place. Okay, sulfur means allotropes of sulfur like monoclinic, rhombic, plastic. Okay, Which one can form hydrogen bond? Okay, if you're talking about oxygen, when the if you're talking about the previous one, then agreed, Faizan. Yes, oxygen, correct. This point, yes, the speciality of oxygen in the form of water or alcohol or acids when it's bonded to hydrogen, it can form very strong hydrogen bonds. Yeah, this is a crown shape arrangement. Hina, yes, we can call it a puckered arrangement. Great. So, except oxygen, all other members are solid. They will exhibit allotropy. Name an allotrope of oxygen. You to named monoclinic sulfur means rhombic sulfur, plastic sulfur, or milk of sulfur. All these are fine. Sulfur people know. Name a O3. Yes, and we'll discuss about its this allotrope O3. Not only about ozone layer alone, we'll also talk about yes, so many correct answers. We'll also talk about the role of O3 as an strong oxidizing agent. Yes, great. Yes. So as we were expecting and as discussed just now, so oxygen will show this anomalous behavior due to its small size, high electronegativity, absence of d orbital, and because the 2p orbital is quite small, no, and at least when suppose oxygen sulfur is also involved, not a problem. At least oxygen has one 2p to spare, so it can form d pi p pi or p pi p pi bonds very easily. It's not possible for the other elements to behave like this. Atomic radii, no tension, no confusion. Who troubled us? Lot of group 13 troubling. Group 14 also troubled us little bit. If you remember, yesterday only we did no. So tin's melting point is least. So such few exceptions are there. Here, no issues. There's a regular increase down the group. Fine. Ionization energy. Yes, no exceptions. That's the greatest satisfaction. Ionization energy. There's a regular decrease in ionization energy down the group. And needless to say, the first ionization energy of oxygen less than nitrogen because nitrogen had that exceptional stability due to its half-filled configuration. You know all those things. Oxygen will show positive as well as negative oxidation state. Mention me or tell me a compound where oxygen shows positive oxidation states. Name some compounds of that type. No. In HF, okay, others wrote OF2, O2F2, yes. In OF2, see, fluorine is the most electronegative element. So say for example, if a person who is like getting the second rank says I am the best, he has to or she has to say I'm the best except the first topper. Similarly, with the first topper fluorine, with the first topper fluorine, it exhibits a positive oxidation state. It can show +1 as well as +2 oxidation state. I would like to know mm, a compound of oxygen which shows -1/3 oxidation state. No problem, no problem, Suman. Happens. Okay, OF2, O2F2. By chance, instead of O, you typed H. No problem. Very good. Ozonides. Potassium ozonide, KO3. Where oxygen shows -1/3 oxidation state. No point in asking anything. All the answers I'm getting. Which question should I ask? Then will I'll not get an answer. No, nothing like that. So sulfur, selenium, and tellurium will show +4 as and +6 states generally. Oxygen will show -2 to +2 oxidation states. +4 states stability increases, +6 stability decreases down the group. Stability of the +4 state increases, but the effective, the very strongly, very convincingly, we can not talk of inert pair effect officially here. So the logic is similar, but according to the textbooks, if you go, they talk of inert pair effect up for group 13, 14, and 15, last element of that. Anyways, due to similar reasons, the plus 6 stability decreases, plus 4 stability increases. Group 16 elements show plus 6 oxidation state with oxygen. Some error. Oxygen and fluorine. Something. Fine. Leave it. Yes, this is irrelevant. So compounds in which the oxidation number is plus 4 or plus 6 are covalent in nature. Give some examples. SF6, sulfur sp3d2, octahedral geometry. SF4, seesaw shaped. sp3d, remember? So in the higher oxidation states, you will see that the compounds show covalent bonding prevalently. Very important, students, this pages. Okay. When they combine with oxygen like SO3, okay, that's what they mean. Okay, but oxygen is also one of the more member, no? So group 16 elements means they should here. I was wondering, this is also group 16 element, fine. They should mention here sulfur, selenium, tellurium. Then Faizan, now it's correct. Now these elements, when they combine with oxygen, when they combine with chlorine, they can actually not only show plus 6, the some error, they can show plus 4 oxidation state also. So much error, I striked it out. Basically, what they try to say is the elements like sulfur or selenium or tellurium, when they combine with oxygen and chlorine, no, they can show both plus 4 and plus 6. Plus 6 more stable. Than plus 4. Now it's okay, Faizan. So many corrections and so many things to discuss. I thought leave it and continue. Fine. Now I would like something important from you. Bond angle. As I explained yesterday, the lone pairs are quite closer. The lone pairs are quite closer, so they will face more repulsion. So the bond angle here will be more, here will be less. Bond angle should decrease. Agreed. Drago's rule. H2S onwards, you're going to use Drago's rule. Agreed. It's in and around 90. If you strictly check the values, you can do that. You will see that it is a decreasing trend. Yes, if you would consider Drago's rule, then H2S falls into the Drago's rule category, and you will see the bond angle to be 90° and here 104. You see the exact values, there will be a decrease. Perfect, very good. So bond angle decreases, moral of the story. Bond length increases because the small hydrogen is not at all very compatible with the large tellurium. So bond angle down the group decreases. Acidic strength increases because it's easier to release the protons because they don't have good compatibility. Bond length increases, becomes large. Bond strength decreases. Thermal stability decreases. TS would be too much. Should I write thermal stability decreases? Reducing nature, the hydrogen would be more available down. Increases. Let's have a look. Bond angle, anywhere you require an explanation, please, because it's a discussion going on. Boiling point, Faizan, boiling point. The problem is the boiling point here is governed by hydrogen bonding. So it should be H2O, which should have the highest boiling point, followed by H2TE because of its large size and strong van der Waals forces, followed by it should be H2Se and then H2S. That's the reason I didn't comment on the boiling point, but you did the right thing by raising that point. Though it doesn't increase, it's water which should have the maximum boiling point here due to hydrogen bonding. Extensive, strong hydrogen bonding makes it difficult to separate the water molecules from each other and separate and convert them into the gaseous state. So water, this is the decreasing order of boiling point. Here the reason is hydrogen bonding. Then size. The next important factor is as size is more, surface area is more electrons, more protons, more interactions, it becomes difficult to separate them or requires more energy to convert them into the gaseous state. Hence this order. Everyone clear? Clear this point? Since boiling point was raised, I try my best. If I missed out, ah, yes, if I miss out some of the chats, it's because difficult to maybe link or manage both. Bond angle, yeah, you apply Drago's rule, the distance also decreases. Bond length, definitely, this very small, this very large, increases. Thermal stability decreases. It's not that stable because of lack of compatibility. So the acidic strength will be more, reducing nature will be more. Important. Similarly, hydrides of group 15, you did know. Similar logic. Once again. Yes. So you get SO2 also, you get SO3 also. As I was telling you, +4 oxidation state, +6 oxidation state is quite prevalent for oxygen. +2, +1, 0, -1, -2. These are more prevalent. By the way, what is this ion? Who can tell me? So these oxides can be formed in the +4 state also. I hope nothing is written here. Again, otherwise I have to erase. No. And +6. Yesterday we learned one thing. Acidic nature is directly proportional to the oxidation state. Greater the oxidation state, greater will be the acidic nature. Acidic state or acidic nature is more if the oxidation state is more. Acidic nature is also directly proportional to the electronegativity. So as electronegativity decreases down the groove, the acidic nature of the oxide also decreases and basic nature of oxide increases down the groove. Clear everyone? The same logic and we are applying it in different groups. Yes. Amphoteric. Okay, this one is superoxide. Amphoteric TeO2. TeO2 actually, honestly, tellurium, what I can recollect is it can act as a basic oxide. Will it react with acids as well as alkalis? I generally deal with oxygen, sulfur, tellurium. I'm always very honest. I can't recollect it being an amphoteric oxide. I thought it to be basic only. Tell me, Faizan, if you know with clarity. So, by the way, till then, TeO2, I thought basic oxide. Yes, correct, Suman. Because the bond pair of electrons are quite close. They say, oh my God, we are so close, there will be more repulsion. To minimize the repulsion, no, a little bit. Say a group of students or some people are standing in some queue or line. There's a lot of rush. And you can manage till someone touches you. If that, then you will like push. That's what is happening. Little push, the bond angle here is little more, and hence bond angle decreases. Vanadium will behave differently because I'm talking about group like P block. When we talk about D block, they will show different anomalous behavior, some with logic, some without logic, we can deduce. Okay, I'll definitely find it out. According to me, right now, TeO2 is basic oxide for sure. Okay, SeO2 is a solid. O3, SO2, these are all gases. Reducing property will is decreasing from SO2 to TeO2. Why do you think is it so? SO2 is reducing in nature. TeO2, okay, TeO2 came here, oxidizing in nature. I can just tell you this. Non-metals, this is a non-metal sulfur, tellurium is a metal. Non-metals will be very stable with higher oxidation states because that increases its acidic character. Metals will be quite happy with its lower possible oxidation states because that makes them more basic. Lone pair will suppress the bond angle or not. Suppress. No, I'll tell you the, the thing is here as well as here. Both of them suppress the bond angle from its expected value. Yes, I got it now, Suman. Wait. So here, without the lone pairs, like in CH4, the bond angle is exactly 109.5. Here, bond pairs being replaced by lone pairs, yes. The answer, Suman, is yes. The bond angle here is 104.5 because due to the presence of lone pairs which occupy actually more space and hence undergo more repulsion, the bond pairs try to come closer. And if you're asking two things, yes, Nandana, inert pair effect TeO2 agreed. So I repeat first, let me answer Suman. Suman, yes. The when bond pairs are replaced by lone pairs in the regular geometry of a molecule, bond angle decreases than its expected bond angle value. Bond angle decreases than its expected bond angle value. Number one. But when I have to compare the bond angle of H2O and TeO2, so CH4 and H2O, when I have to compare, bond angle is exactly 109.5 or 109 degree 28 minutes. And when these bond pairs, two of them are replaced with lone pairs, you'll see that the bond angle becomes 104.5, less than the expected value because seeing the big lone pairs, they get scared and they come closer. Hence, lone pair will suppress the bond pair angle or not. The answer is yes, Suman. Now done. Next, now both oxygen and tellurium are sailing in the same boat. Both have two lone pairs each. Now, how do you compare the bond angle? Now we will look into, we can't look into the lone pairs because same problem here. The size is little more, but the problem is the same. Two lone pairs here, two lone pairs here. So what happens is the bond pairs are quite close in the case of oxygen here. In the case of tellurium, they are quite apart because the electronegativity difference between tellurium and hydrogen is much less than the electronegativity difference between oxygen and hydrogen. Here the bond pairs, in the case of oxygen, they are much closer. They are quite far. So this gap you'll get more and this is less. So compared to TeH2, H2O will try to little bit, not that much, because if it goes much, this scary lone pairs are standing. Little bit as compared to TeH2, H2O, little bit goes apart. And hence H2O TeO2, H2O has a greater bond angle. CH4 H2O, CH4 has a greater bond angle because there are no lone pairs to trouble it. So yes, the answer is lone pairs do suppress the bond angle. TeO2, yes, I can think in terms of inert pair effect, but inert pair effect makes the lower oxidation state generally see. Without inert pair effect, it's +6, which is mostly existing. With inert pair effect, it should be +4, which is more stable. It's already +4 here. So in a way, yes, but after inert pair effect, it's should be +4 more stable than +6 due to inert pair effect. +4 more stable than +6 due to inert pair effect. It's already +4 here. Now, how will we justify? We'll just say that Tellurium will be even happy to go to the +2 state also. Lower the oxidation state on the central metal atom or ion, it will try to behave as an more stable basic oxide. For non-metals, greater the oxidation state, greater the acidic strength of its oxide. For metals, lower the oxidation state, lesser will be the acidic character, more will be the basic character. In that sense, also you can say, because this is the way I can't justify inert perfect. You yourself think, if I say yes for that, yeah, similar logic. But if I say it's +4 here, and +4 is supposed to be the more stable state than +6. Fine, good. Good analysis, good discussion is going on. So ultimately, Te +4 wants to go to +2 state. That's the thing. Want to become more basic and hence acts as an oxidizing agent because it wants to get reduced to this. In that sense, its basic character will be more. S2O, I'm sorry, SO2. SO2 is reducing in nature. Do you know why? +4 here. If it can just jump to the +6 state, sulfur in the +6 state is very, very stable. Sulfur is very stable in +6 state. Tellurium, more stable in +2 state than +4 also. Out of +6 and +4 better. +2 and +4 plus. Yes, yes, yes. Where the history. Tellurium in the +2 state. Very good. Sulfur in the +6 state. So SO2 is reducing in nature. TeO2 is oxidizing in nature. So a lot of things in redox are required here, right? Let it come, and then one by one I'll explain. See, these elements, as we move down the group, their size increases. So when their size increases, it's easier for them to bond to fluorine than iodine. Both small compatible. Both large horrible. One small, one large, chalega. Okay, fine. So when the element is large in size, and except oxygen, others are pretty large. So those large atoms would be more compatible with fluorine due to its small size. Like we go for back bonding and say, if it's 2p 2p, well and good. 2p 3p, okay. 2p 3d, okay, no problem. 2p 4p also to some extent I'm ready to manage, but 3p 3p I'm not ready to manage. I'm not ready to show a stable pi bond here because both are large in size. Effective pi overlap will not take place. Due to similar reasons, halides would be more stable when they are fluorides, then chlorides, then bromides, and then iodides. So SF4 is a gas, SeF4 liquid, TeF4 solid. Very obvious. As the size increases, van der Waals forces increases. For the alkyne also, as you go down the group with increase in size, the forces become stronger and the physical state slowly changes from gas to liquid to solid. Okay, they form dichlorides and dibromides. Let them form everything. Let them try. Let them form difluorides also, no problem. But if you talk about the hexahalides, six groups are present, students, around the central atom. I will favor only hexafluoride formation because others would be too large. Large, not allowed. Small, best. Small, large, okay, chalo, manageable. Large, small, okay, manageable. Large, not manageable. So only hexafluorides are the stable halides. SF4 a gas, SeF4 a liquid, TeF4 a solid. Same reason, as you go down the group, size increases, attractive force increases, physical changes from gas to liquid to solid. All these hexafluorides are gaseous in nature. Hexafluorides cannot be formed by oxygen, non-availability of d orbital. Yes, this is not very commonly asked or something. Just know that. So here these monohalides, like instead of SF, it exists as S2F2. That's more stable. S2F2 structure I'll draw. Only one structure I'll draw, huh? Like this. Comment on the hybridization of the sulfur here. So they're just trying to show that these dimers will undergo disproportionation. So here the oxidation number of, comment on here selenium is 0. Here it is plus 4 and here plus 1. Tellurium plus 2, indium plus 2. Actually these it can be okay where they actually. We don't have to worry much about because not much questions are asked from these parts. Or I can ask you to focus in the last minute is more on oxygen compounds and sulfur and compounds. As I've read that the lower oxidation states is, is good enough for these metals to survive. Fine. sp3. Yes, I'll be telling you an honest thing. We are not much bothered about these people, honestly, tellurium, because a lot of questions are not asked from that sulfur. You can see the previous years. That's the reason. Generally, lower oxidation states would be favored for metals because they can form stable basic oxides. Higher oxidation states for non-metallic oxides because those acidic oxides would be stable. Yes. So you can see KClO3 on decomposition produces O2. These metal oxides Ag2O, HgO, PbO2 liberating O2. But remember, these give you metals. Ellingham diagram, when it comes, I'll explain. PbO2 gives only PbO and O2. H2O2 undergoes disproportionation, you know very well. And if you want to prepare oxygen, you can take to the electrolysis of acidulated water. You add some small amount of acid or base as a catalyst to water, and on electrolysis, oxygen gas will be produced. Students, any not only inorganic, anything, any topic. Post your doubts in Telegram. Post your doubts to me once again. I'll send you so that during your exam time, I can help you out. I can do my best for you. Colorless total gas. Why is it paramagnetic? I can't see it paramagnetic. Which chapter should we go if we want to see it paramagnetic? Which theory should we apply? Very good. Very good. MOT. We should draw its molecular orbital diagram and then you can find it paramagnetic in nature. Very good. O2 is the most important component without which combustion reactions cannot take place. So students, if we take a sulfide ore, we'll come to that chapter. If we take a sulfide ore, sulfides will react with oxygen or undergo combustion with oxygen to produce ZNO and SO2. Ethene will also combine with oxygen to produce CO2 and H2O. Hydrocarbons will undergo combustion to give CO2 and H2O. You just now saw this. So O2, you are involved in so many combustion reactions. We understand you're very, very busy. In Ostwald's process, catalytic oxidation of ammonia to nitric oxide and water. There also oxygen is required. Oxygen is basically required for everything. In the contact process, which we'll see in this chapter, SO2 is converted into more stable SO3 in the presence of vanadium pentoxide catalyst. Oxygen, you are very special. You're required for so many reactions. I just mentioned the important one. Yes. Students, simple oxides, MgO, CaO, Na2O, Al2O3. Mixed oxides, Pb3O4. One more different example I'll give you than what's written here. Pb3O4 is summation of PbO plus PbO2. In PbO, I'm sorry, 2 PbO we have to take, no? Pb3O4. So here I'll to place plus 2 state. Two leads are in plus 2 state. One lead is in present in plus 4 state. So mixed oxide because it contains mixture of these two oxides. 2 PbO plus PbO2. 2 FeO, no, only 1 FeO and 1 Fe2O3. 1 FeO, Fe3O4, yes. So we have mixed as well as simple oxides. Acidic oxides. When you add water, they form acids. Basic oxides. They will react with water to produce bases. Basic oxides, when you add water, they'll form the respective bases. Acidic oxides, you add water, they form the corresponding acids. Except I told no, someone was like right now also discussing about some when when it comes to D block, all the things don't behave in a similar way. That's the reason we studied blockwise. Yes. Though we agree that generally non-metals form acidic oxides, these metal oxides, there are certain metal oxides of the D block. We'll study D block. MnCr vanadium. These are metals. In spite of being metals, these metal oxides can form, these metals can form acidic oxides. The metals generally form basic oxides. Non-metals generally form acidic oxides. These metals like manganese, chromium, vanadium, these are metals, but still they are forming acidic oxides. Important point to be noted. They are metals, but they are not forming basic oxides. They are still forming acidic oxides. Now, I still don't remember tellurium being amphoteric in nature. Definitely, I'll look into more into tellurium. I didn't give importance to it. Yes. But otherwise, amphoteric oxides are the ones which react with both acids as well as bases. Aluminium oxide, zinc oxide, tin oxide, lead oxide. B25, yes. Yes. The only point is we are not discussing about that right now because I thought we'll take it in under D block. Agreed. Vanadium pentoxide. True, true, true. But like taking out specifically things of S and P block and after that moving to D. Agreed. Neutral oxides, as we discussed, CO, N2O, NO, they will not react with either acids or bases. Vanadium pentoxide, I agree, but I want to discuss about it in the D block. Agreed. But tellurium oxide is what I have to find out because I'm not sure whether it's an amphoteric oxide or not. Students, do you have any class after this? So I can extend it 5 minutes? Or you don't? You have? What class do you have? Next. Okay. Can I continue at least for the next few minutes so that we can little take care of the syllabus? Yes. Students, your and my both my homework, mine homework more. Let's find out tellurium oxide. I never gave it importance. This tellurium oxide. whether it is amphoteric or not. It's no doubt definitely forming solutions which are bases, but whether they can react with both acids or bases, we are supposed to see. Now, ozone is an allotrope of oxygen. How is it prepared? See, ozone is very unstable. It contains O2 plus O, right? A nascent oxygen. Would it like to be formed from the stable O2? Which is stable? O2. Something is stable and something is forming is unstable. Is it true? Is it possible? What do you think? O2 is stable. Stable would like to do something and become unstable. Would you like to lose marks and get low score in an exam? You don't, right? So if this is supposed to happen here forcibly, the reaction will be endothermic and only 10% conversion rate, 10 to 15%, as given in different books. Only 10 to 15% of the oxygen which you take will be converted into O3. So when silent electric discharge is passed through oxygen gas, you will see only 10 to 15% conversion to the less stable O3. And even this process is endothermic in nature. So maximum 10, as given in the books, 10 to 15% they write, conversion takes place. Let's draw the structure of O3. 1, 2, 3, 4, 5, 6. The central oxygen is sp2 hybridized, and you can see a trigonal planar geometry. Geometry trigonal planar. If I talk about the shape without the lone pair, it's bent or V-shaped. This ozone is highly unstable and acts as a strong oxidizing agent. You know why? O3 is O2 plus O. So this extra O, it can supply and itself become very, very stable. Properties. It's a pale blue gas. In the liquid phase, it's blue in color, while it exists as a violet or blackish violet colored solid crystal. Of course, it is a stronger oxidizing agent than O2 because it has an extra nascent oxygen to spare. So, diamagnetic, as I drew, you saw it bent shape and you didn't see any unpaired electrons, so it's diamagnetic and bent in shape. A stronger oxidizing agent than O2. O3 can oxidize H2S to S. Sulfur in the plus 4 state to sulfur in the plus 6 state. It can oxidize H2S from minus 2 state to 0 state. Sulfur from plus 4 to the plus 6 state. Oxidizing agent, it will force the other atom to lose its electron. Sulfite again, plus 4 to plus 6. Minus 1 to 0. Again, it will cause the oxidation of the other element. Very important, important. Fe2 plus will be oxidized to Fe3 plus. Mn plus 6 will be oxidized to Mn plus 7. Manganate to permanganate. Most I2 to HiO3, not HiO4. Be careful, HiO3. Iodine in the previous case also with HNO3 also gets oxidized to iodic acid, not periodic acid. It's HiO3, not HiO4. PbS to PbSO4. Hg. A little bit talk about tailing of mercury. What happens is when O3 reacts with Hg, only a part of it, not completely, only some part of Hg gets converted into its oxide and gets oxidized to Hg2O. Now what happens is some Hg remains. Only a part of it gets oxidized to Hg2O. Remaining Hg remains, and mercury doesn't stick to the glass, students. So when you're just pouring it, you'll see a tail like thing of mercury coming in, grayish colored. It doesn't stick to the glass and separates out. Mercury will now be separating itself from Hg2O because a lot of mercury is still left, excess reagent. The separation of this excess mercury from Hg2O, and since it doesn't stick to the glass like this, it just comes out. And sometimes you pour some glycerin or something, you'll see, just like a tail, the sticky liquid comes out. That's known as tailing of mercury. Ultimately, O3 oxidizes Hg into Hg2. So O3 and H2O2 are used to remove black stains of old paintings. Like H2S in the air oxidizes lead in the paint to PBS. Paintings turn black, because lead in the painting will react with H2S in the air. The same reason silver articles get blackened. H2S in the air will combine with silver, and Ag2S, which is formed, is black in color. So now if you want to restore it, treat it with O3 or H2O2, any one of the oxidizing agent, and the black painting will be converted again into white because PbSO4, which is formed, is like this -2 and this +6, white in color. The last slide today, because only 2 more minutes are left. So what happens, students? The supersonic jets release NO. This NO reacts with O3 because O3 is an oxidizing agent and oxidizes NO into NO2. So as a result of this, the ozone layer in the stratosphere is getting depleted. The harmful UV radiations which was blocked by this ozone now comes directly on the Earth's surface. Skin cancer, blindness in animals, living beings, all these are the side effects of ozone layer depletion. So till ozone we discussed today, and remaining we will discuss in the next class. So the next class, can I ask you some questions on group 13, 14, 15 and 16? We'll complete 16 and after that. Is that okay with you? All of you? Okay, fine. Thank you everyone then. Bye. I'll upload these notes. Bye. Goodbye. Thank you.
Thank you, ma'am. Thank you, ma'am.
Thank you all.